Hey guys, my name is IBM and I'm still taking you through the past paper questions of magnetic fields and electromagnetic induction. I think this is going to be this is mostly going to be part 11. This is part 11. You can check through right from part 1 up to part 11. The past paper questions are available. You can leave a comment about this. And there's another document which has solutions which have been clearly typed. You can also find that on the website, or you can write to me and I tell you how to obtain the document. So question 26, a bar magnet of mass 250 grams is suspended from the free end of a spring as illustrated here. The magnet hangs so that one pole is near the center of a coil as shown here. The coil is connected in series with a resistor and the switch. So it means there is a possibility of power being dissipated in the resistor as thermal energy. The switch is open. The magnet is displaced vertically and then lowered to oscillate with one pole remaining inside the coil. The other pole remains outside the coil. So now that the magnet is oscillating, it is moving up and down. It means that the coil cuts um, the magnetic field of the magnet, and since the magnet is oscillating, that means there is a change in magnetic flux linkage between the coil and the magnetic pole. At time t equals to 0, the magnet is oscillating freely as it passes through its equilibrium position. So at t equals to 0, it is oscillating freely. At time t equals to 6.0 seconds, the switch in the circuit is closed. So when the switch is closed, it means now we have a continuous loop of the coil. We have a complete circuit for the coil. So if the switch is closed and yet the magnet is moving up and down, that means there is going to be an induced e.m.f in the coil. The variation with the time t of the vertical displacement y of the magnet is shown. So at 6 seconds, when they close the switch, we see that the amplitude of oscillation now starts decreasing. In other words, there is damping, and the damping is actually light damping here, because you see that the amplitude decreases gradually. Initially, it was free oscillation because the amplitude was constant, it was 1.5 centimeters. And after 6 seconds, when they close the switch, it now decreases. That means now the energy of oscillation is being lost or is being dissipated, which is making the oscillations to die out. For the oscillating magnet, use data from the figure to calculate two significant figures. The frequency. Of course, this is in simple harmonic motion. So in the first 6 seconds, when it is oscillating freely, you notice that we have 1, 2.5 cycles. So this is 1, this is 2, this is a half. We have 2.5 cycles. In the first 6 seconds, we have 2.5 cycles. So that means the time for one cycle, which is the period, is going to be equal to 6 seconds divided by 2.5 cycles. That is the time for one oscillation. And you and me know that the frequency is equal to 1 over period, which is going to be now 2.5 divided by 6. So 2.5 divided by 6. So this is 0.416 recurring, that is 0.42. So the frequency is going to be 0.42 Hertz. The energy of the oscillation during the time t equals to 0 to time t equals to 6 seconds. Of course, this is part of simple harmonic motion. So the energy of oscillation is equal to a half m omega squared. Since this is a graph of y against time, so this is going to be y naught squared. Remember the equation for total energy for simple harmonic motion, a half m omega squared x naught squared, where x naught was the amplitude. Now that here displacement is represented by y, I will just use y naught for amplitude. But you also know that omega is actually 2 pi f. Omega is 2 pi f, and f is 2.5 over 6. So I'm just now going to substitute. Energy is going to be equal to half times the mass. The mass was 250 grams, which is 0.25. Where there is omega, I'm going to put the exact value of frequency, which is 2.5 divided by 6, but this should be squared. But this is omega is 2 pi f. Sorry, I need to add 2 pi f here. So omega is 2 pi times f, which f is 2.5 over 6, and this should be squared. Then times y naught, which is the amplitude, and the amplitude is 1.5. The amplitude is 1.5 centimeters. So this is going to be times 1.5 times 10 to the power of minus 2, and this should be squared. So I'll just check with my calculator. So a half is 0.5 times 0.25 times, I'll open brackets, 1.5 exponent minus 2, but this is squared. Then I'll have times, open bracket. I can simplify this. This will be 2.5, that is 5 pi over 6. So I will say 5 pi divided by 6, but this should be squared. So I'm getting 1.93 times 10 to the power of minus 4, which is approximately 1.9 times 10 to the power of minus 4 joules. State Faraday's law of electromagnetic induction. We have already mentioned that Faraday's law deals with magnitude. So we say the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So many times I want to avoid restating these laws, but because I need to refer to them when answering the other parts of the equation, that's why I restate them sometimes where it is inevitable. So use Faraday's law. Because I knew I was going to use Faraday's law, I had to repeat this equation, even though we have already stated the law early on. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. So use Faraday's law and energy conservation to explain why the amplitude of the oscillations of the magnet reduces after time t equals to 6.0 seconds. So we have seen that after time t equals 6.0 seconds, the amplitude now starts decreasing because they have closed the switch. In other words, they have completed the circuit here in which the coil is incorporated. So by all means, there is going to be induced EMF now that we have a complete loop, a complete circuit, a complete loop which can allow free movement, free flow of current. There is going to be an induced EMF because the coil is going to be cutting the magnetic field of the moving magnet. So the coil cuts the flux, call it field, of the moving. The coil cuts the flux or the field of the moving magnet, thereby inducing an EMF, thereby inducing an EMF and thus current in the coil. So now that the coil is cutting the magnetic field of the magnet, this is inducing a current in the coil, which current is going to flow to the other end. There are notes that we have a resistor here. So current flowing through this resistor is going to dissipate energy because there will be power dissipated here, where power is I squared R, and therefore there will be energy dissipated here, which will be I squared R times T. So because power is energy over time, so energy is power times time. So the energy dissipated is going to be equal to I squared R times T. Therefore, the energy which is dissipated here is derived from the oscillations of the magnet, and therefore it means because energy is being wasted as heat in the resistor, the oscillations of the magnet are going to die out. Okay. So the coil cuts the flux or the field of the moving magnet, inducing an EMF and thus current in the coil. That's a current in the coil. The induced current in the resistor causes a heating effect. The induced current in the resistor causes a heating effect, and the thermal energy or the heat energy is derived from the energy of oscillation, is derived from the energy of oscillation of the magnet, and so oscillations die out with time. Because the energy of oscillations is what is actually converted into electrical energy in the coil, as the coil cuts the magnetic field, that electrical energy is now going to be flowing through the resistor, and therefore it is going to cause a heating effect in the resistor. So because energy is dissipated as heat in the resistor, and yet it is derived from the oscillations of the magnet, then it means the magnet is going to now slow down. The oscillations are going to die away with time. State the type of field or fields that will give rise to the force acting on a moving uncharged particle. The particle is moving but is uncharged. So now we have three types of fields to talk about here. We have the gravitational fields, the electric fields, and the magnetic fields. Gravitational fields will act on anything as long as it has mass, whether it is charged or it is not charged, whether it is moving or it is not moving, as long as it has mass. Therefore, here we expect a gravitational field because the particle is going to have mass. So we have gravitational field. Number two, electric fields only act on anything which has charge, whether it is moving or not moving, as long as it has charge. Since this one is not charged, we don't have an electric field. So it means for the second one, we have an electric field. Because An electric field, a force acts on a charged particle in an electric field. So an electric field acts on anything or gives rise to a force on anything which has charge. Whether it is moving or not moving, the force will exist as long as it has charge. Then a magnetic field uh, acts on anything which has charge as long as it is moving, and it should be moving at a non-zero angle. It should be moving at, or it should be having, this direction of motion should have a component perpendicular to the magnetic field. In other words, the particle should not be moving parallel to the magnetic field. So here, it must be having a charge. And of course, the magnetic field acts on a particle which has a charge, and the charge must be moving at an angle to the magnetic field. The angle should not be zero. So state the type of field or fields that will give rise to a force acting on a moving uncharged particle. If it's uncharged, it is only the gravitational field. A stationary charged particle. So because the particle is charged, there's an electric field, but also has mass, so there's also gravitational field. There's also gravitational field because it has mass. A charged particle, first of all, it has mass, so there's a gravitational field. And it is charged, so there's an electric field. But it is moving at any angle to the field, so assuming the angle is not zero, so it also has a magnetic field. So a magnetic field only gives rise to a force on a charged particle when moving at a non-zero angle. If the particle is charged and moving at a non-zero angle, then there will also be a magnetic field. So you have only one for the first one, electric and gravitational for the second one, then magnetic, electric, and gravitational for the last one. An electron, mass m, charge minus q, is moving at a speed v in a vacuum. It enters a region of uniform magnetic field of flux density B as shown here. Initially, the electron is moving at right angles to the direction of the field. Initially, it enters at right angles because the field, so if it enters at right angles, when it enters the magnetic field, now the field exerts a force because it was initially moving at right angles. So when the velocity is perpendicular to the magnetic field, the particle experiences a magnetic force. Explain why the path of the electron in the magnetic field is the arc of a circle. We have already answered a similar question. When a charged particle enters perpendicular to the magnetic field, the magnetic force is always constant and always perpendicular to the velocity of the particle. So the force does not change the speed, there will be no change in speed, there is no change in kinetic energy, there is no work done, and therefore the magnetic force just provides centripetal force or centripetal acceleration. So the magnetic force is constant and always perpendicular to the velocity or to the direction, to the perpendicular to the velocity or direction of motion. So the speed is constant, or you could say kinetic energy is constant, or you would say there is no work done. When the kinetic energy does not change, there is no work done on the particle. On the particle is an electron on the electron. So the magnetic force only provides centripetal force or centripetal acceleration. So the magnetic force will only provide centripetal force, or it will provide centripetal acceleration. Okay, derive an expression in terms of the radius r of the path for the linear momentum of the electron. Show your working. So of course we know that the magnetic force provides centripetal force. So I'll simply say magnetic equals to the centripetal force. So magnetic force is B, Q, V, and the centripetal force is m v squared over r. So this means that BQ times r is the same as m times v. 1v cancels. Of course, we know that mv equals to momentum. So this implies that momentum equals to BQR as required. The diameter of the cross-section of a long solenoid is 3.2 centimeters, as shown in the figure. So this is a long solenoid. It has 85 turns. A coil C with 85 turns of wire is wound tightly around the center region of the solenoid. The magnetic flux density B in a Tesla at the center of the solenoid is given by the expression. So the magnetic flux density is B equals to pi times 10 to the power of minus 3 times I, where I is the current in the solenoid in ampere. Show that for a current I of 2.8 amperes in the solenoid, the magnetic flux linkage of the coil C is 6.0 times 10 to the power of minus 4 Weber. So you and me know that flux linkage is equal to NBA or ban. So the number of turns of the coil is 85 times the magnetic flux linkage B, which is pi, times 10 times 10 to the power of minus 3 times I, where I is 2.8, then times the area. Of course, we know that the area equals to pi r squared. So this is going to be times pi times the radius. They gave us the radius of the diameter of the coil is 3.2 centimeters, of course. The diameter of the coil is this. So the radius is 1.6. So I'll simply say times 1.6 times 10 to the power of minus 2 squared to change it to meters. So we can check with our calculator. So 1.6 exponent minus 2 squared, what is that? 1.6 exponent minus 2 squared times pi squared, because there are two pi's, times 85 times 2.8 times 1 exponent minus 3. So I'm getting 6.0 times 10 to the power of minus 4. But the examiner always wants to see the answer which rounds off to what has been given. So this is 6.01 times actually 13 times 10 to the power of minus 4 Weber, which rounds off to 6.0 times 10 to the power of minus 4 Weber. The current I in the solenoid in B is reversed in 0.30 seconds. It is reversed, which means it moves from one maximum to another maximum. Therefore, the time just to reach one maximum is half of this time here. Calculate the mean EMF induced in the coil. So we know that the EMF induced equals the rate of change of magnetic flux linkage. Rate of change of magnetic flux linkage. So this is going to be equal to, of course, this is NBA divided by time. But of course, the time is going to be half of this. That is 0.30 divided by 2 because the current is reversed. So it means it leaves one maximum to another maximum in 0.3 seconds. So if it is just from 0 to a certain maximum, it should be a half of this. Therefore, the induced EMF is going to be, of course, NBA is 6.0 times 10 to the power of minus 4 divided by the time, which is 0.30 divided by 2, which is actually the same as 6.0 times 10 to the power of minus 4 times 2 divided by 0.03. So 6.0 or 6 exponent minus 4, then times 2 divided by 0.03. Sorry, it is 0.3. That is, sorry about this. So this is 0.3, which is giving us 4.0 times 10 to the power of minus 3. Okay. Oh, sorry, this is 4.0 times 10 to the power of minus 3 volts. But since they have millivolts here, then it means I'll rub off this exponent. The current I in the solenoid in B is now varied with the time t as shown in the figure here. So the current is varied as shown here. So we notice that here the current is constant. And remember, whenever the current is constant, it means the magnetic flux linkage is constant. So the induced EMF corresponding to that current would be 0. Wherever the current is constant, the induced EMF corresponding to it is 0. Whenever the current is constant, the induced EMF corresponding to it is 0 because the induced EMF is directly proportional to the rate of change of magnetic flux linkage. If the current is constant, the magnetic field is constant. A constant magnetic field implies that the magnetic flux linkage is constant, so the rate of change is 0. Okay, use your answer to show on the figure 9.3 the variation with the time t of the EMF E induced in coil C. So we are using the answer in C, which is the EMF, that is 4.0. So for the first 0.3, I think 0.3 is here. 1, 2, 3, 4, 5. That is 0.1, 2, 3 here. The EMF 1, 2.5. The EMF was constant. I mean, the current was constant. The induced EMF is, remember, the EMF induced is directly proportional to the rate of change of magnetic flux linkage, which is going to be directly proportional to the gradient of the graph of current against time. So whenever the gradient is 0, it means the rate of change of flux linkage is 0 because the flux linkage is constant. So the induced EMF there is going to be 0. So we have seen that between t equals to 0 to t equals 0.3, the induced EMF is 0 because the current was 0. Then between 0.3 between 0.6 and 1.0, the induced EMF is also 0. 0.6 and 1.0, the induced EMF is also 0. Then between 1.6 to 2.0, the induced EMF is also 0 because the current is constant. So for those points, it's going to be a horizontal line along the x-axis. I'll try to draw this line. Try to increase the font. Okay, so for those values of time, the induced EMF is 0. Then between 0.3 here and 0.6, the current changes or the current is reversed. The current I in the solenoid in B is reversed in 0.30 seconds. So the current is reversed in 0.3 seconds, and we have seen that the induced EMF corresponding to that is 4.0. So the current varied from 2.8 positive to negative 2.8 in that time. The induced EMF corresponding to that is 4.0 milliteslas. Then let's check the gradient on the other side. So here it is between 1.0 to 1.6. You notice that the gradient here, the change in current is the same. In the vertical, it is 2.8 minus negative 2.8. But on the x-axis, the time it is taking to change is actually 0.6. Yet this time, the change on the vertical axis was 2.8 minus negative 2.8 over 0.3. So it means the gradient on the left-hand side is twice the gradient on the right-hand side. The gradient on the left-hand side is twice the gradient on the right-hand side. And also, the gradient on the left is positive. So this is negative on the left, and this is positive. So if we say the EMF here is positive, if we say the EMF here is positive, we would say the EMF here is negative, or the other way around. If I say the EMF represented by this gradient is negative, the EMF represented by the other gradient is going to be positive. So they should not have the same sign because the gradients have opposite signs. So what is very important to note is that the gradient on the left-hand side is twice the gradient on the right-hand side. That's number one. And remember, EMF is directly proportional to the gradient. So if the EMF represented on the left-hand side is 4.0, the EMF represented on the right-hand side is going to be half of 4.0. Because EMF is directly proportional to the gradient of this current, because it's directly proportional to the rate of change of magnetic flux linkage. Okay, so since they didn't give us values for E, I'll just use the number of squares. Remember, the EMF represented between 0.3 to 0.6 is twice the EMF represented between 1.0 to 1.6, but they have opposite signs. So I can say, let me represent this by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to represent this EMF with 10 small squares. With 10 small squares, the graph is in the box here because this is 0.3. Then I'll represent this because they have opposite signs. This will be at the bottom and the gradient is going, the EMF is going to be half of the other one. So this is going to be half. Okay, so the logic behind these graphs is very easy. When you master the concept, you don't even need to think a lot. These 4 marks are very, very easy to get. So that is the graph. You could also draw the graph the other way around. In other words, you could make this to be at the bottom. You could make the first section to be at the bottom, and you put the second section at the top. It doesn't matter. It is still accepted. But for now, I will leave only that one there. Okay, I want part 11 to stop here. See you in part 12. Until next time, bye bye.